Hello, my friends. Welcome to discussion today. I'm here in beautiful Richland, Washington at a conference, and I thought, well, we can't really skip another day of not moving forward. So today we're going to talk about states of matter and phase changes. Now, you should have some guided notes to go along with this lecture. So if you want to get those guys out and get them taped in, if you haven't already, that would be fantastic. If you need to pause the tape, pause it here. Let's get started. So today we're going to talk about properties of solids, liquids, and gases. And then what happens when we basically heat a solid and see where it goes into a liquid and gas and why. So to start with, we're going to start with properties and phases of matter. So in the video we're about to watch, we're going to try to push our finger through a solid, a liquid, and a gas, and we're going to compare what it feels like to do both of those. You won't be terribly surprised.
So let's see how different phases of matter deal with getting things pushed through them and see how that varies. So here again, I've got that steel ball. It's a nice solid, and I try and push my finger through it, and not surprisingly, I can't push my finger through it. In fact, if I push really hard, it tends to hurt a lot. And that's the same thing for my desk here. If I try to stab my finger through it, it will not happen. It just hurts my finger. That hurts. If I try that same thing with water, so I've got this little cup of water here, you can see that, oh, not surprisingly, I'm actually able to push my finger right through the water, and I can move it around, although I do feel some resistance. If I try to walk in a pool, it's like really hard to walk because I'm pushing through all that water. Now, let's try that one last thing, and let's try gases. Can we push our fingers through gases? And sure enough, our finger goes right through gases in all directions, and it's super easy, much easier than water. And when I do this, I can feel the air. I can feel some like breeze on my finger, resisting my finger. And if it was a hurricane, 200-mile-an-hour winds pushing against my finger, I would say, oh, it's a significant force and it's harder to push through. But still, I can push through it. Fascinating stuff.
Now what you saw there is that the desk, water, and air was the order in which it was harder to push through. So really hard to push through the desk, easy to push through water, but you can still have some resistance. And then air was super duper easy. So then the question we have to ask ourselves is, why is this trend this way? So in order for your finger to push through something, what must those molecules, we've been calling them particles, but the word molecule is a really good synonym. It means the same thing as particle. So what do the molecules have to do in order for your finger to push through something? And of course, the molecules have to be able to get out of your way. So if you push on something and it gets out of your way, you can push through it. Just like if you're going into a crowded gymnasium or something and you're pushing the people and they don't move, you can't really push by them. You can only push by them if they move out of your way. That's the same thing with molecules. So from that observation, we can tell that solids must have particles that can't move out of the way, while liquids and gases can move out of the way. So go ahead and on your note sheet, make sure you're catching up with these different points. If you need to pause the video, go ahead. All right, so the next video we're going to watch is a syringe. We're going to fill that with air, a gas, a solid, and a liquid again, and then we're going to try and compress them and see what happens. And when we're doing that, we're going to answer this question: which states of matter are compressible, which are not? So as you watch the video, go ahead and answer that question.
So to start with, let's look at the compressibility of solids. I've got this little steel ball here. I'm going to drop it right into my syringe. I'm going to push it down, pushing all the air out, and get right down to the top of that ball. And then I'm going to try to push it and compress it. And at first I think, oh, it feels like the plunger moves. But when I look really closely, what I'm really seeing is just the black rubber part of the stopper is what's being compressed, not the steel ball. So it looks like solids like steel are really not very compressible or not compressible. It's hard to get them to squeeze anymore, and that's probably not very surprising. How about, though, what if we switch over from a solid to a liquid? So on this one, I'm going to take a syringe. I'm going to draw up some liquid. I'm going to do that super cool doctor thing and tap out all the air. Boop. I love that. And cap it real quick. So now, fantastic. Now the water can't get out. I'm going to try and compress this. Let's see what happens. Oh, It's really hard to do. Like it doesn't feel like it's moving at all. And even if I feel like I'm getting some movement with it, when I look closely, it's really just that, again, that black stopper getting compressed a little bit, just like with the solid. So like solids, liquids seem like we can't compress them. Push really hard and they don't get smaller. All right. And the last one we're going to try is with that third phase of matter we're talking about, and that's a gas. So I'm going to take my cap off the water. I'm going to fill this guy with air, right? So I'm just going to go like this and fill with air. Ooh, totally chock full of air now, right? And then I'm going to push on it, and I'm going to see, ooh, air is pretty easy to compress at first, but then it suddenly starts getting really, really hard. It still looks like it's empty, but still hard to compress. But compared to water and steel, solids and liquids, it's super easy to compress. It can cut it to almost half the volume before it gets even very hard at all. So there's gases. Cool beans.
And of course, we found that gases are compressible, liquids and solids are not compressible. And what does this tell us about the amount of space between molecules in a solid, liquid, and a gas? So of course, if you're compressible, then there must be a lot of space between you because you get closer together. If you're not compressible, there must be little to no space between you. And what we found was that liquids and solids are both virtually incompressible, and that if they have any gaps in them, they have tiny gaps. We know there are spaces between them, but those spaces must be extremely small, not big gaping like gaps in between the particles. Unlike gases, who we can easily squeeze them to half their volume, so those spaces must be relatively large in gases and extremely small in solids and liquids. So now we're going to look at another video about how changing the shape of the container affects solids, liquids, and gases.
Let's take a look at how the three phases of matter are affected by the shape of their containers. Let's start with solid, for example. I've got this steel ball again right here. And I'm going to take this steel ball and I'm going to drop into this round bottom container. And let's see what happens to the shape of the ball when I do that. And not very surprising. So the steel ball stays a sphere shaped, even though it's in a round container. It didn't glom out to be the shape of the container. It kept its own shape. Now I'm going to do something really crazy here. And I'm going to put this round steel ball, I'm going to put it into a square bottom or rectangular bottom container. And let's see what happens to the shape of the ball. Oh, and tragically and not surprisingly, it stayed as a sphere. So it looks like solids are not affected by the shape of their container. That's not very surprising. Let's take a look at liquids though. So we have a liquid. I have it here in this round bottom container called a cup, and it's nice and round. I see the shape of the water is tapering in like this. It's got a round bottom and a round top. And then I'm just going to pour this into this, square bottomed container, rectangular container. And sure enough, what I end up with is no longer round water. Now I've got rectangular water, even with these little scalloped edges. So it looks like liquids do take the shape of their container and that they don't have a defined shape for just themselves. Now, how about gases? What do gases do? Well, this one's hard to show because gases are pretty much invisible to us. But if we imagine the gas in this container and we change the shape of the container, that gas is going to completely fill up that messed up looking shape just like the liquid would. So gases and liquids take the shape of their container, solids retain their own shape. Awesome.
And of course, an ice cube or a solid, a steel ball, will retain its shape. It doesn't change its shape when you put it in a different container. Liquids, on the other hand, do. They flow into the bottom of the container and take the shape of the container. And then gases don't just flow to the bottom of the container, they fill up throughout the whole container. Now we're going to take a look at a video about how changing the volume of the container affects the volume of the object. So again, we're going to look at a solid, a liquid, and a gas.
So how do changes in volume affect the three phases of matter? Let's take a look. So again, I've got my steel ball here. I'm going to put this bad boy in here. I'm going to put the thing out. I'm going to push it down. Get as much of the air out as I possibly can. And then I'm going to very quickly take my cap here, and I'm going to cap this syringe so nothing can get in there. And I'm just going to pull it down. So I'm going to make the container it's in, I'm going to make it bigger. See, oh, sure enough, that ball stays its same shape and size no matter how big I make the container. Not that surprising. All right, awesome. That's that one. What if, though, we switch that and we were to go over to water and say, okay, I'm going to draw some water up here. I'm actually going to push it in with the atmosphere, but it's neither here nor there. I'm going to do that doctor thing, get the air bubbles out. Woo, get the air bubbles out and cap it. And then I'm going to pull down on it. And while it's hard to do, when I pull down on it, notice how the water doesn't fill the entire volume. It's just where it used to be. So it looks like its volume remains constant, even though the volume of the container changes. So again, liquids don't expand to fill our containers. All right? But what about gases? What if I put a little bit of air in here? All I do that, I just go like this, and air just pushes itself right in for me. And I go like this, and I cap it, and then I pull this down. So before the water, when we did this with water, the water actually fell to the bottom, and there was this gap of space up above. Now, if we were to go in there and breathe, what do you think? Do you think that all the air has fallen down to the bottom, or that it's spread throughout the whole container? If you said spread out throughout the whole container, you are absolutely right. It is spread across the entire container. So unlike liquids and solids, gases tend to expand to fill their entire container, every nook and cranny. Awesome, good job.
And of course, the ice cube, the volume stayed constant. It doesn't expand when you make the container bigger. It just sits where it sits in the bottom in its nice little shape. Now, liquid does flow to the bottom and take the shape of the container, but if you make the container bigger, the liquid doesn't spread out and fill the whole container. It just stays in the bottom. Unlike a gas will actually, when you expand the container, it will fill the container. Well, we use the word fill, probably shouldn't use the fill. It will spread out so that there are particles evenly spread throughout the entire container, although the particles will be farther apart now. So is that filling it? I don't know. They just spread out. So at this point, I want you to use this chart in your notes and fill it in, all these different pieces in here for the summary properties. Give yourselves a few minutes to do that. Check with a neighbor, talk to each other, figure out what you're doing, and then we'll come back to this. Okay, so for solid, can you push through it? Nope. That's because they are stuck in place. Can you compress it? Nope. That's because there's very little space between them. Will it take its shape or take the shape of the container? It keeps its own shape because the particles are stuck in place. They can't move around and flow into the container. And it also your volume remains constant because, again, the particles are stuck together so they can't spread out through the container. Can you push through it? Yes, for a liquid, you definitely can push through it. Can the molecules move around? They can move around. That's our evidence. When you push on them, they get out of your way instead of staying in place. Can you compress it? No, you cannot compress it. That means there must be very little space. In reality, you can compress a solid and a liquid, a super tiny amount with huge amounts of pressure, but we consider them both non-compressible. Will it take the shape or keep its shape? It'll actually take the shape of the container because, again, the particles can move around. So when the force of the earth pulling down, that thing we call gravity, pulls on them, they tend to fall down to their lowest places and take the shape of the container. Does it keep its volume? And it does. The volume remains constant. So the rationale for this is that the particles are still stuck together, just like in the penny drop experiment when we had that big glob of water that was like flowing over the edges, like, you know, those particles on the edges that should have just fallen off were actually sticking in there and sticking together. So gases, can you push through them? The answer is absolutely yes, which means they must be able to move around because when you push on them, they get out of your way. It would be crazy if gas wasn't like that. Like, well, we wouldn't know what moving around is because we would be stuck in place all the time. Can you compress it? The answer is absolutely yes. And what does that tell us? Well, that tells us there must be a lot of space between the particles. And will it take the shape of the container? Yes, it takes the shape of the container because they're just moving all over the place. And does it keep its volume? It does not. It takes the volume of the container. So that tells us that gas particles must not stick together very well because they're constantly spreading out all over the place. They just go in all directions. Whereas a liquid, they stay clumped together. I mean, they can flow around each other, but they can't totally escape each other. Whereas a gas, they can. Now we're going to use this Venn diagram to place, to write in those properties from before. And remember, we're looking for here in this space are properties that are solid only. Here, liquid only. Here, gas only. In this space, properties that are shared by solids and gases. Here, and here, shared by liquids and solids. Here, liquids and gases in this region right here, liquids and gas properties. And then here are properties that are shared by all of them. Now, you have to be kind of creative to get some of these in here, but you can find some. There definitely are some really good ones that we've learned in the past that maybe aren't in the table. But definitely try and get as many properties as you can in these Venn diagrams, see where you end up. Go ahead and pause the video and have some time to do that. All right, so let's start right here in the middle that's common to all of them. So what are some things we may have put here? And we may have said something like, hey, you know, they're all made of particles, so they're made of matter. So that's a good thing to put here, right? So you may have said something like, hey, they have mass. All of these three things have mass. And there's a lot of things that can go here, you know, that they all have some kind of temperature. They have kinetic energy. They are made of matter, which is really like saying particles and mass, all really kind of the same thing. All right, now things that are just solid properties. So here we're thinking, what's something that's only solid? Let's start somewhere easier. Let's start between liquids and solid. What are some common properties between them? And here we might put something like not compressible. You guys probably can't read that. I'll write bigger, I apologize. So not compressible. The next thing we're going to put here are particles are close together. So close together. I'm only writing slightly bigger. I don't have much room. So not compressible, close together. You know, one big one for all of them is that they're moving in some way. We've learned that as well. So not compressible, close together. Hey, for the liquid-gas combination, so here's some things that we can say that they take the shape of their container. Ooh, let's put up here actually, keep volume. We should probably check this later. Keep volume. Here, this is the take the shape of the container. So take shape of container. Let's see what else. And then the gases are, of course, compressible. So, oh, the writing is getting worse. Oh, come on, PowerPoint. It is compressible. Gases are compressible. These guys, not compressible. Keep volume. There's really no properties that are solely liquids. Liquids are like a combination of properties from gases and from solids. And there is one, and here's a solid one. It's only solid, and it says, whoops, I should say keeps shape. So it keeps its own shape, whereas liquids and gases do not. And again, liquid is, you know, a mixture of properties of gases and solid. It's like a solid. Sometimes it's like a gas in some ways. Now phase changes. So let's talk about melting and freezing. So here's a new key term for us. This one right here called intermolecular forces. Whoops, I'm getting ahead of myself. So here, these intermolecular forces is a new key term for us. We're going to use this a bunch. So far, we've talked about particles being sticky or sticking together. Well, that force that holds particles together is called an intermolecular force. And these forces are attractive between particles, and it's this thing we've been calling stickiness so far. Now, molecules in the solid can only vibrate back and forth because those intermolecular forces, that stickiness, is so strong that they can't bust away from each other and move around each other. They're literally holding each other in place. So you can imagine a particle inside of a solid, right? So you have this chunk here, and there's particles all around it, holding it very strongly, and they're holding each other, and they're all just kind of freezing, holding each other in place, stuck. Which means all they can do is vibrate. They can vibrate back and forth, up and down, left and right, but they can't actually switch positions with other molecules. So they really never go anywhere, which is kind of cool because if you think about like on the surface of your desk, those particles, those molecules on the very surface of the desk are the same molecules that were there yesterday. They're not switching places. Kind of a cool idea. Now, as we heat a solid, just like all things, their kinetic energy increases and they start moving faster. And as they move faster, it becomes harder and harder for them to hold on to each other. And they start hitting each other harder and pushing each other farther apart, vibrating really fast. And that's a whole expansion thing. But here they're going faster and faster. Now, if they keep heating them, they're going to be vibrating so fast at some point that they're not able to hold each other in place. And then suddenly they're going to be able to start switching places with each other. That makes it just like vibrating so crazy while they're, and they switch places. And when a lot of them can do that place switching thing, you suddenly go from being a solid to being a liquid. And that's what the melting process is. So that means a solid has turned into a liquid. So ice into water is an example of melting. Now the video you're about to watch, we're going to take a look at what happens when we heat a solid. As you watch that video, describe what happens to the metal particles as they're heated and turn into a liquid.
All right, so what I have for you here today is this metal called solder. It's used to make electrical connections and stuff. So one of the neat things about solder is that it's a pretty soft metal. It's a mixture of tin and silver, this stuff is. And that makes it soft and it has a fairly low melting point. So let's see what happens when we do some heating of it. So what I'm going to do is I'm just going to put it in there like so, right? So you see this whole thing of solder sticking out. And then I'm going to just, I'm just going to heat it. I've got my little blowtorch here. Oh, that's a good sound, isn't it? I'm just going to go here and heat this thing. And now, of course, as the metal atoms, the particles of metal in the bottom of the solid here heat up, they start vibrating faster and faster. Now, they're still holding each other in place, and that's why it's a solid. So it's a big chunk of metal like this for that reason. But as they heat up, they start vibrating so fast, faster and faster, that it becomes hard for them to hold each other in place. And there'll be a time when they're going so fast that, ooh, can you see it yet? I think its process has already started. That goes so fast that they actually can switch positions. And when they get to that point where they're actually switching positions, you go from being a solid that you can't stick your finger through to a liquid that you can. And you can see now that we're taking that whole stick of solder down into a pool of liquid. And now we have, just like any other liquid, we have a liquid metal. And what I'm going to do is just pour it out here, right here on my table. And you can see that glom of liquid, just like any other liquid. You can move it around. It flows around stuff. You could push your finger through it if you wanted to get burned badly enough. But what you end up with is this great puddle of super hot liquid solder. Now, of course, as these bad boys slow down, they're starting right now. As they slow down, they're not moving as fast. So those intermolecular forces at some point are going to be able to grab back on. And they're always grabbing each other, but they're going to be able to grab strong enough that they can actually hold each other in place. And that's because they're now moving slower and are easier to hold in place. Not because the forces got stronger, but because they're moving slower now. And this is still too hot to touch, but let me bring it up for you so you can kind of see it. Bam, that's our little splatter of solder. You can see where it burned the board there too. Awesome.
Okay, so these particles vibrate faster and faster until they can move around and switch places. And once they do that, they're a liquid, and they do things like flowing. Now describe what happened to the metal particles as they are cooled and turned back into a solid. Hopefully here you're describing as they cool, they slow down. And once they get so slow that they can actually not just stay close together, but actually hold each other in place. They're strong enough to hold each other in place. Bam! That's called freezing when they're stuck in place again. For this following statement, you're going to say whether it's totally true. If not, you're going to identify the parts that are incorrect. So when a solid heats up the molecules vibrate faster. This makes the intermolecular forces weaker, allowing the molecules to move around each other. So take a few minutes, 30 seconds here to talk to your partner or your table mates about this question and say, do you think it's totally true? And if not, which parts are incorrect? How would you change them to make them true? Pause the video and take that time now. All right. Hopefully you guys can see here that this first part is true. Wow, they vibrate faster. That's good stuff. Whoops, need my pen on. The part that's not true is this next part. It's not that the forces get weaker. So this part, the intermolecular forces get weaker. That is not the problem. The problem is that because the particles are moving faster, they're harder to hold on to. So if you imagine someone walking by you and you're a friend of yours and you're like, hey, and you grab their shirt to stop them, right? Hey, I want to talk to you. You grab their shirt. You can stop them. They're not moving very fast. But if they came sprinting by and you reached out to grab their shirt, even though your hand is just as strong as it used to be, they would rip away from you or their shirt would tear or something. Something bad would happen. And that's because, not because you're weaker, that force isn't weaker, it's because they're just moving faster. So here this has more to do with how fast they're moving and not how weak the force becomes. The force we can assume stays really constant. All right, let's keep going. So we've got evaporation and condensation to talk about. So now that we have a liquid, we have particles that can switch places, so when you push on them, they get out of your way. The molecules are moving fast enough to move around, but they're still held close together in clumps, that blob of water, by these intermolecular forces. Now, as you heat the water is moving around faster and faster and faster, switching places, going all over the place, faster and faster and faster. At some point, they're going to be moving fast enough that they're actually able to totally break away from each other and escape the surface of the liquid. That process is called evaporation. And this is when a liquid turns into a gas. For example, water turning into steam when you boil it, or just water evaporating at the table. It's those particles breaking away into the air. And we had talked earlier about how evaporation is really the same fundamental physical process as dissolving is, except when a liquid dissolves into the air, we call it evaporation, whereas when a solid dissolves into liquid, we call it dissolving. Now, boiling is a term we use when we reach the fastest evaporation point. In fact, the liquid's evaporating so fast when it's boiling, it actually evaporates inside the liquid and forms bubbles of that evaporated gas inside the liquid that then float up to the top, pop, and shoot the gas into the atmosphere. So that's all boiling is. It's just super fast evaporation. Now this demonstration we'll do when I get back because you're going to have to feel this to be able to get a good sense of it. Now our last set of phase change is what's called sublimation and deposition. Now you may be familiar with sublimation. That might be a familiar word to you. Sublimation is well, let's talk about it. So when the boiling temperature, so the point where it boils at, is less than or equal to the melting point, a solid will turn directly into a gas. So instead of melting to a liquid first, it just goes from solid straight to gas. And this is what's called sublimation. So you're familiar with dry ice not having a liquid state. Dry ice is an example of sublimation. So it goes straight from a solid straight to a gas. The particles just break off and fly out. They don't turn to a liquid first. Now water will sublimate too at low pressure. So if you get a really low temperature and pressure, you get some ice and reduce the pressure, it won't turn to a liquid first when you heat it up. It'll just disappear like dry ice does, but only at really low pressures. And freeze drying is actually an example of the sublimation process. So when we freeze dry something, you get it really cold first, you freeze all the water inside of it, and then you put it inside of a vacuum chamber and pump all the air out so it's super low pressure. And then as you heat the food back up, like I don't know, strawberries or whatever you're trying to freeze dry, and you heat that back up, the water, instead of turning to a liquid and sticking inside the stuff, just breaks off as individual particles and sublimates out. So you get a super duper dry fruit when you're done instead of just partially dry. It's much faster and easier. Now, deposition is the opposite of sublimation. So sublimation is the process where the solid goes straight to a gas. Deposition is when it goes from a gas straight back to a solid. And we can see this. It's a really common thing, even though we don't probably talk about it very much. Whenever you see frost forming. So if that frost forming from water in the air, if it was turning into a liquid first, you'd see a droplet of liquid that would freeze into like a hard little ball on the leaf. And sometimes you'll see that because dew will form, then it'll get cold, and it'll freeze the dew. But more often you see like crystals, like they're like little shards of ice. And that's because it's directly forming from a gas to a solid and creating that little pretty crystal that forms on there. So that kind of frosted look is deposition. Also, snow is the same thing too. So snow isn't the gas in the clouds, the water vapor in the clouds, the gas water in the clouds forming into a ball and then freezing, of course, because that would give you hail. It's the actual water in the clouds forming into a solid instantaneously. Right when they touch, they're a solid. So they form these really cool crystals instead of globs of frozen water. All right, at this point, we've done a lot. We've covered a lot of ground. I'm sorry, it's been in a video. It's probably taken forever. But what I want you to do now is write a summary of phase changes. Here, you're going to draw a picture of what a solid looks like. Here, you're going to draw a picture of what a liquid looks like. And here, you're going to draw a picture of what the particles of gas look like. So when I say, let me re-say that. So here, picture of what the particles of a solid look like. So you're going to draw circles for the particles. And you're going to show, are they clumped together? Are they on the bottom spread out? Are they spread through the whole container? Is there a lot of space between them? Is there a little bit of space between them? And then on each of these lines, you're going to write the name of the phase change. So let's do the first one together. So from solid to liquid, let me pick up my pen real quick. From solid to liquid, you would say, okay, if I go from a solid to a liquid, oh, I call that melting, I believe. And then I would say, yes, I'm right. It's melting when it goes from solid to a liquid. You're gonna name all of these lines. And on top of that, you're gonna actually do some more. You're gonna name, oh, get my pen going again. You're gonna name this one as well. Boom. Solid straight to a gas, skipping liquid. And also you're gonna name this one. Gas straight to a solid, skipping liquid. You should be able to get the names of all of those phase changes on there. All right, so there's something like this. So in your solid, you should show this organized structure here with them all stuck together. They can't move around each other, so they're stuck in place as a clump in the middle. You should have a liquid. You should have it, oh, it's all gooed down to the bottom and flow down to the bottom. And then gases are pretty evenly spread throughout and moving really fast. And here's a description of some of the things. And there are those phase changes, right? So we have melting, evaporation. You could have put boiling here as well. That would have been a good one to put here as well. Condensing is the opposite of evaporation, and freezing is the opposite of melting. Now, solid to gas, of course, that one's sublimation. And then gas to a solid is deposition. So those are all of those on there. All right, for each of the lists down below, I want you to, whoops, sorry about that. I want you to name the phase change associated with it. So melting, freezing, evaporating, condensing, sublimation, deposition. Write those down. All right, go. All right, so hopefully you had liquid to solid and you said, hey, that means it is free. Whoops. Doing the bottom one first, I guess. Gas to a solid is called deposition. Then freezing for the next one up. Solid to a gas is sublimation. Gas to a liquid, so that's like steam turning back to water, is called condensation. Solid to a liquid, well, that's called melting. Liquid to a gas, there's two names. There's slow process, which is called evaporation, and the super fast process is called boiling. Awesome, so far so good. And this we'll take care of this next slide the next time I see you. Great job today. Way to hang in there and be troopers. I really appreciate it. We'll get back to doing science together on Friday. This has been my last meeting this year, so I look forward to being back in the classroom every day from this point on. All right, my friends, have a nice one. We'll see you.